The question is the coherent state is a squeezed state? Now we are looking for the answer of this question because uh, if the coherent state is a squeeze state, then what will be the condition? If it is not a squeeze state, then what will be the condition? So note, I have written this statement. A squeeze state of the radiation field is obtained if delta xi whole square is less than 1 over 2, 1 over 4. And it means that I means 1 and 2, and it shows that if we have delta x 1 square is less than 1 over 4 and delta x2 is less than 1 over 4, then for this condition the state will be a squeeze state. If this condition is not satisfied for any state, then it means that this will not be a squeeze state. So now we are looking for the this question, that the coherent state is a squeeze state or not a squeeze state. So I will start from this equation A, because delta x1 whole square, which is equal to x1 square average minus x1 average whole square, and I have to show the delta x1 square as less than 1 over 4 and delta x2 square as less than 1 over 4. If this condition is satisfied, then this coherent state will be a squeeze state. If this is not satisfied, then it means that this will not be a coherent state. So starting from this, I will take a coherent state, because the average is taken x1 square, and here the state is a coherent, so then I have to apply the coherent state from this side and this side, because this is the expectation value. And x1 square, we know about x1 square, x1 which is equal to 1 over 2 a plus a dagger. So here we put the value, so this is 1 over 4 plus a dagger whole square. And similarly for the this 1 over 2 a plus a dagger, and this is a whole square because this is a square. Now 1 over 4, and here also 1 over 4, because this is a square, and if I take out this from this square, then this must be 1 over 4. So I can take 1 over 4 common here, and then I expand this a plus a dagger. So a square, a dagger square, a dagger plus a dagger a, and the coherent states can be applied. And then here this and this can be average of this and this. This is a very simple method that I can apply here. And further, I can take this a square, this and this and this separately with the coherent state. So this is a coherent state of a square and this a dagger. But here a dagger, I can put the value for a dagger, a dagger which is equal to 1 plus a dagger a. So I have I have taken this 1 plus a dagger a, the value, and this can be obtained from the commutation value of this. So, and then I can take the expectation value of a dagger a, and similarly, if a is applied on this coherent state, then we must the eigenvalue alpha, and a dagger is applied on this state, we must have alpha star, and the whole square as it is. And here, if I apply a square on alpha state, then we can get alpha square. It is because if a is applied on this state, then one time we can get alpha eigenvalue and a alpha, and if we apply again, then alpha square and alpha, and then the alpha state is the normalized state, so it make 1 and alpha square, and from here we can get alpha star square, here alpha and alpha we can get 1, and alpha a dagger a. If we apply 1 the annihilation operator, we can get alpha, and after we apply the a dagger, then we can get alpha star. So from this we can get alpha star alpha, and similarly for this case as well, alpha star and alpha. And now expand this square, so we get the alpha square plus alpha star square plus 2 alpha star alpha. And now I can apply this minus to this, and write the whole expression like this. You can see that here alpha square can be cancel out with this positive and negative, and this is positive and this is negative, this is positive and this is negative. Then we can get only 1, and 1 can be multiplied with 1 over 4, so we can get 1 over 4. It means that delta x1 whole square, which is equal to 1 over 4. And similarly, if we take this for a delta x2, then delta x2, which is equal to x2 square minus x2 whole average square, and apply the same method, but here you can put x2 will be equal to 1 over 2 iota a minus a dagger, and putting the value of here just like this, and try to calculate this thing, because it is very easy. The same process you can do. And alpha square plus alpha star square minus 1 minus 2 alpha star alpha minus, and this, and here you can see this alpha, and this can be cancelled out, this can be cancelled out with this, and this can be cancelled out with this. You can get minus 1 here, and here iota, if you take iota, then you have minus 1 over 4, and here you have an iota, but if we multiply this with this, then this is one thing is missing, because here this is iota square. So if this is iota square, then we can get minus, and then minus minus 1 over 4. So from here we get two things, delta x1 which is equal to 1 over 2, and delta x2 is equal to 1 over 2. If I take the square root, then the condition is delta x1 square is less than 1 over 4, and delta x2 square is less than 1 over 4. But here we get delta x1 square which is equal to 1 over 4, and delta x2 square which is equal to 1 over 4. So it means that the condition is not fulfilled for a squeeze state. So we can say that the coherent state is not a squeezed state, because we must satisfy this condition.